Assalamu alaikum wa rahmatullahi wa barakatuh. We are discussing chapter 5, nonlinear programming 1, one-dimensional minimization methods. Very basic few elimination method is already discussed in the last class. Today we are going to discuss one more method that is known as dichotomous search method. So okay, so idea is very simple. This is one of the elimination methods. So in the elimination method, what we try to do is we are given with a range of values of x in between. In some notation, they have used xs and xf, or also in some books, the range or the interval given interval of uncertainty is a and b. So whatever you prefer. Bottom line is somehow we have to pick points among them. So based on the criteria, whether you're going for minimization or maximization, based on that, some of the interval will be discarded. So that is why it is an elimination method. So basically, our ultimate objective is to obtain the x optimal that will correspond to our f optimal. Okay. So what we are trying to do here is in each of the methods and dichotomous or Fibonacci or golden section method, in all of the three cases, basically we are just introducing two experiments or two values of x1, two values of x1 and x2, then say this is a minimization problem. Minimization problem. And we can see that fx1 is smaller than fx2. So we can take the decision that, and obviously, one of the criteria given at the beginning of this chapter is this is a unimodal function. So basically, we can only have one maximum and a maxima or minima in a given interval. So since we are moving in this direction, value is reducing and we're looking for a minimization problem, we can easily discard this portion of the interval. So our new interval is going to be interval of uncertainty will be basically in between a and x2. Okay, so graduate, and then again we have to take two more points. It may depend on whether x1 will be existing or not, and from method to method it can vary. So bottom line is, if you have this scenario, again two more points is taken, and if they are equal, then we take the half, the middle one, average of the middle one. If one of them is smaller than the other one, then we take, say we have something like this. So we can take the decision that our new range will be from, say if this is your x3, so x3 in between x3 and x2. So gradually we are going to reduce this portion we discarded. So gradually we are going to reduce the interval. Ultimately, a certain exact precision value will be given on this interval, say that 10% of exact value. Okay, so somehow we have to link the 10% with our formulations so that we can check this also known as stopping condition. Okay, so whenever our interval is actually 10%, within the 10% range, then we can actually, we have to stop. So every iteration, after every iteration, you have to check this condition of accuracy as well. So in this method, these are more general thing we have discussed here so far. Now we'll try to discuss the case or the scenario with our dichotomous search method. So for that, the method is very simple. Basically, what we are going to do is whatever the interval given in maybe our range of the interval of uncertainty is starting from XS to XF. And what we're going to do is we take a half at the middle of it, then a small interval, which is very, very small, will be also taken. So this is exactly at the middle. And this distance, we also, the distance between the interval is known as L0. So this is exactly L0 by 2. Here, it's L0 by 2. And then a small value has been assumed, del by 2, del by 2, this distance here. Okay, so in this distance, we'll try to find out 2 points. The first one, say x1, and the second one is x2. So we obtain x1 in this particular case, basically L0 by 2 initial interval, half of the initial interval. Then we take minus del by 2, which is very small variation. So in general, we take a value. If the value is incognito, it is always to be assumed to be 0.001. And the other point x2 will be L0 by 2 plus del by 2. Okay, so at these 2 points, x1 and x2, we have to plot the function. So if the value is something like this, then if it is a minimization problem, we are going to discard these values. We are going to discuss this portion of our interval. So our new interval will be from XF to X2. So new interval will be XS to X2. So this is subjected to minimization. Okay. Now, if it is maximization subjected to maximization, then the new interval will be, in this case. So then we have to discard this portion. So our new interval will be from X1 to XF. So these ideas will be clear more with the relevant solving of the relevant math problems. So now with first iteration, so In first iteration, we can see that our values of the interval of uncertainty after first iteration, what is going to be happening is uh, L0 by 2 plus del by 2. Okay, so this is what we are taking after first iteration. Okay, so how we are finding this? Basically, whether you discard this portion or this portion. So the remaining portion in the first case is basically this. Okay, so up to this is L0 by 2, then we have del by 2. Or in the second case, that is maximization, we have this portion left, and this is basically again L0 plus del by 2. So what about the scenario after first iteration? The final interval of uncertainty is this. So with n equal to 1. So n equal to 2, what will be the scenario? Let me draw it more clearly. So this is our, in some book, they also use A and B. You can also take that notation if you want. There is no harm in it. So this is the middle. So plus and plus and minus. So this minus first, then plus. And we have seen that this may be a maximization problem. So we can discard the lower value. So basically, we can discard this portion. So our new interval is going to become this segment. Okay, so this segment is our new interval. So we can also say then that this will be our new A, and this will be remaining as B. Then again, we have to take the middle of it. So say this is what we call L1, or a general term will be more helpful is LAB. So LA, it will always remain LAB because we're just defining new values of A and B every time. So again, what will be the scenario? LAB by 2 plus, again, a plus minus of basically del by 2. So, but whenever we are taking the final interval, so then what will be only the value, the plus will be remaining, because every time, as you can see, that L0 then plus. So L0 is also LAB in the first case. Okay, so now after second iteration, n equal to 2, what we are going to get is LAB by 2 plus del by 2. So as you can see, LABB is nothing but the previous one that we had, and that is L0 by 2 plus del by 2. And we have to take the half of it. With that, we have to add a del by 2. Similarly, in the third case, when your n equal to 3, so previous, which is this, we have to take half of it. So half of the previous value of L0 by 2 plus del by 2 plus del by 2 plus again additional small change del by 2. So as you can see here, what we are going to get, in the first case we had L0 by 2 plus del by 2. In the second case, L0 by 2, L0 by 4 plus del by 4 plus del by 2. Third case, what we're going to get is L0 by 8 plus del by 8 plus del by 4 plus del by 2. So can I say that we can write in this way L0 2 to the power 3 plus del 2 to the power 3 plus del 2 to the power 2 plus del 2 to the power 1. So if we have n number of iteration, then what should be the scenario here? For the third iteration, 3, 3. And also a continuation of 3 to up to 1 in case of your del. So we can say that our final value of L, that is final interval Ln, okay, is going to be L0, initial interval by 2 to the power n, plus del divided by 2 to the power n plus del 2 to the power n minus 1 and goes up to finally del by 2. And this is, we can write in this way, basically L0 by 2 to the power n. You take common of del, then you have 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus goes up to 1 by 2 to the power n. Okay, so this is a geometric series, and solving that will give us, okay, if you want, we can also solve the series. So we're just assuming that Sm is our series, that is 1 by 2 plus 1 by 2 square and goes up to 1 by 2 to the power n. So now if you multiply this with half, then we have half Sn equal to 1 by 2 square plus 1 by 2 cube plus goes up to 1 more, basically 1 by 2 to the power n minus 1. So if we subtract the second one from the first one, then we'll have 1 minus half Sn. So the other terms will be vanished. Ultimately, we'll be left with half minus, sorry, it should be plus here. So 1 by 2 to the power n plus 1. So half of half Sn equal to, you can take common of the half as well. So 1 minus 1 by 2 to the power n. So half and half getting cancelled out. So Sn will be basically 1 minus 1 by 2 to the power n. So our Ln, which is the nth interval or the last interval, will be basically L0 by 2 to the power n plus the rest of them, the summation of the rest of them by taking the common del is basically 1 minus 1 by 2 to the power n. So we can easily figure out how many times we have to do the iterations from using this formula basically. So if certain value is given, that your value has to be, your value given is basically, they're saying that 10% of exact value. So what does it mean is basically the final interval that we're going to get, we have to take half of it. So half of the final one, so half of the ln with the ratio of the top first given interval. This one has to be lesser than 10%. Okay, so why half? Because every time we're actually taking half of it, and then with small variation, which is del. So approximately half every time. So that half is actually going to determine your the closeness of your result. So that is why half of the final interval, that is ln, to the ratio, the initial ratio, that has to be within 10%. So, and also this is our stopping criteria, as we have said. So this thing will be more clear with the example that has been given. So let's start solving the problem. The solve problem example 5.5. So this is a minimization problem. So minimize f equal to x minus 1.5. The initial interval given, initial interval of uncertainty. So we can call it L0 is basically 0. Actually, the interval should not be L0. So interval is basically 0 and 1. And what is L0? We'll coming back to that. And also it's mentioned that your value has to be within 10% of exact value, 10% of exact value. So basically our interval, now let's try to solve this one. So what is our initial interval? Initial interval we express in this way, xs comma xf, or in some other book, a comma b is basically 0 and 1. And what is L0? L0 is xf minus xs or b minus a. In this case, 1 minus 0 is 1. So this is our initial interval. Now, what is our first value? The first value, first two assumed value will be x1 equal to, basically a common formula is there, x1 equal to always a, or your xs, which one you take, plus L by 2, okay? LAB by 2, we call it LAB by 2, plus, first one should be minus, minus del by 2. And then our x2 has to be equal to a starting value plus LAB by 2 plus del by 2. So let's apply this and check how to calculate the value. So basically x1 will be A is initial value 0 plus LAB by 2. LAB is in the first case, LAB and L0 is the same thing. So it will be 1 by 2, then minus 0.001 by 2, and 0 plus half plus 0.001 by 2. So ultimately it will be 0.4995 and 0.5005. So our next thing that we have to do is we have to calculate these two values. F x1, and if you calculate the value, we are going to get, and the value correspond to this one will be minus 4 minus point minus 0.49957, and f x2 will be basically minus 0.50025. So now plot it to check the value. This is a minimization problem, so keep in mind. So this is your A and B. So A is 0, B is 1. We have taken a value that is, we're just making a larger separation to understand, but they're actually, as you can see, the points are very close. So one of them is this, and the other one is this. Okay, so this is our x1, this is our x2, and x1 is nothing but 0.4995, and x2 is 0.5005. The x1 function value at x1 is minus 4.9957 and minus 5.50025. So as you can see, the value of fx1 is greater than fx2. So since it is a minimization problem, so we have to discard this portion here. Okay, so this will give us the new interval. That is new AB. So now we can also call this one as our new A. So which will be basically x1, and B is basically 0.4995 and 1. So we have to start from these values in the next one. So the two values we have to take is, first of all, the new A. B is same, new A is 0.4995. Okay, so what will be the next values of, so x3 will be A. So this time A is changed, so plus LAB by 2 plus minus del by 2, and x4 will be A plus LAB by 2 plus del by 2. So here new, so we don't know the values of, now A value is 0.4995, no doubt about it. New LAB is basically 1 minus 0.4995, that is 0.45005. So, and also del is always that value of 0.001. So new value is becoming 0.4995 plus 0.5005 by 2 minus 0.001 by 2. Okay, so everything is same except plus will be there, and the values that we are going to get here is 0.74925. A slightly larger value has to be taken, otherwise our values will be, otherwise we cannot differentiate. The values will be too close, the function values. Okay, so the other one will be 0.75025. So calculate the function values fx3 and fx4. So fx3 will be, just put the value that 0.74925, which is the x3 value, then 0.74925 minus 1.5. So this will give us minus 0.5624994375. And here 0.75025, 0.75025 minus 1.5 will give us minus 0.562499, then 9375. As you can see, we have a different value from here to here. Almost the values are very close to each other. So that is why we have said we have to take a larger number to differentiate the value. And also one vital question we haven't answered here, and we, in each step actually have to check, or this is one option, or basically what should be the value of n, what should be the value of iteration, say number of iteration, how many times you have to repeat. So two way we can deal with it using the formula that we have derived, and from the given exact values of percentage, we can directly calculate the value of n. So that many number of iteration we have to go, or in each step we have to check the condition of the accuracy, which is simple, which is basically 2 1 by LAB by 2 divided by L0, that has to be lesser than 10%, that is 0.1. So in the last one also we haven't done that. So in the last one also we have to just figure out what will be the interval, but we haven't checked the condition of the accuracy. So at the end we should add that one. Okay, so basically we're writing here, even though it has to be at the end. So LAB by 2 divided by L0 is to be 0.1. So LAB and L0 in the first case is same, which is 1. So basically half 0.5 is lesser or so the condition says that 0.5 has to be lesser than 0.1, which cannot be true. So the stopping condition is not verified, or the exact value accuracy is not achieved. So that is why proceed to next iteration. Okay, so in each step you can do that. This is one thing, or what you can do is in the very beginning you can apply this formula, that is ln by L0, ln by 2 by L0 has to be lesser than equal to 0.1 exact value. So you know the formula for ln is basically L0 by 2 to the power n. In the formula also you have 2, so 2L0 you can keep, plus 1 minus del, don't forget the del 1 minus 1 by 2 to the power n. So you apply this formula here with 0.1, then you are going to see that the value of your n will be approximately 2.5 around. But and our we are going to get something like this, approximately 2.5. So we can say that the next closest value is n equal to basically 3. So that is why it means that we have to go for 3 iteration. So either you go with this one and then just follow the step, how many iteration you have to go, or after each of the step, you can check this criteria, whether to proceed to the next one or not. As long as the condition is not true, we have to proceed, and whenever the condition becomes true, we have to stop there. So we know from the formula that we have to go for third iteration. So this is only the second one. So you can also write second iteration here. Iteration 2. So now in this case, the condition is LAB is 0.5005 by 2. L0 is 1, so 0.1. So as you can see, it will be almost 0.25, 0.25, 0.1, which is still not true. Not true. So we have to proceed to next iteration. Okay, so also before proceeding to the next iteration, we have to take the decision first. Now here, which one is smaller? This is smaller. So this is x3, which is 0.74925, and this is x4, slightly higher. X4 is basically 0.75025. And our function value here is fx3 is higher than fx4. So we can say that we have to discard this portion, discard a to x3, and our new interval New interval will be x3 to b, which is 0.74925 to 1. Okay, so last iteration, because we know that we have to do up to 3 iteration. Basically, your diagram will be something like this. Your new A value is still 1. A is 0.7492925. And we have to take the other two values. It is x5 and x6. So x5 will be A plus L AB by 2 plus minus del by 2. X6 will be A plus LAB by 2 plus del by 2. And if you plug in the values, new values of A as well as LAB will be basically 1 minus point. LAB will be 1 minus 0.74925. So if you plug in the value, new A is 0.74925. So it will give you approximately a value of 0.874125. Here it will be 0.875125. So 4125 or 5125. And corresponding values of fx5 and fx6. We'll just calculate and you're going to get minus 0.5470929844 and minus 0.5468437342. So now which value is higher? 547 and 546. So 547 and 546. So definitely you can see that in this case, your fx5 is smaller than fx6. Okay, so your new interval of uncertainty this time, which one is smaller? This is smaller than this one. So we can discard this portion, basically. So our new interval of uncertainty will be 0.74925 and 0.875125. Okay, so this is what we call new values of A and B. And since we have to do only 3 iterations, so we can stop here and we can figure out the middle of it as an optimum point. So x optimum will be half of 2, which will be 0.8121875. And corresponding f optimum value will be approximately, it's better to use the approximate formula here, will be minus point, just plug in the value into the function 558632748. So this is the solution of your dichotomous search. So you can either take the number of n, the number of the iteration first, or in each step you check whether the stopping condition is arrived or not. Okay, so see you in the next class with a new method.